Okay, we are on module 2 on chapter 3 and 4. Okay, you can see we started on chapter 3. I uploaded the file for last Monday, September 20th. You can go and look at it. You should be able to start doing question and answers for chapter 3 now. It's somewhere here, question and answers here. So you need to work on chapter 3 now. Okay, I'm going to finish chapter 3 to chapter 3, slide number. We gone over some of the material last class period. We talk about sun's radiation. We are talking about ozone, last thing we talked about. So I am going to look into ozone now in detail and UV radiation that cause damage to skin. Yeah, you are showing in here the interpreter for people who cannot hear. Okay. All right. I'm going to continue from there. I can see you there. All right. There are 3 types of UV radiation: UVC, UVB, and UVA. UVC is the strongest high energetic UV radiation. It causes oxygen bond to break in diatomic oxygen molecules. That also helps in the reproduction of replenishing ozone layer. UVB is partially absorbed in the atmosphere. UVC never comes onto Earth to a significant degree because it's absorbed by oxygen atoms and oxygen molecules. UVB is partially absorbed by a stratosphere ozone layer that breaks up the ozone. So some could come where the ozone layer is thin, or there's a ozone layer, there's a hole in the ozone layer. So we have to be careful about ozone layer. UVA is the least energetic UV radiation. It penetrates deep into skin, causing damage to underlying tissues. So there are 2 web pages. You can go to PDF form of the PowerPoint, then click on anti-aging creams legit video on sunscreens if you use it right. So you can watch videos on them. Now we're going to talk about certain aspect of UV exposure. Although some UV exposure is needed for production of vitamin D, UV produce vitamin D on the skin that's required to certain metabolic functions. Too much UV radiation, even though it is helpful, producing some vitamin D in the body. It can cause eye diseases, cancer. The diagram here shows disease burden and exposure to UV radiation on the bottom axis. As you increase the UV radiation, low amount around C cause skeletal diseases because less exposure to sunlight. Vitamin D insufficiency, insufficient formation of vitamin D is in that range. So the benefit of UV reaches at optimal point in the middle, P, minimum risk. But as you increase the UV radiation exposure, then the harmful effect take over. Therefore, there's an optimal exposure. People who don't spend time in the sun should start thinking about taking vitamin D. So because they could be getting not enough vitamin D. Skin cancer can appear at any age, but it is more many years after repeated excessive exposure has stopped. So there's a balance between exposure here. UVA is the one that we had to worry about, not UVB and UVC. Those are stopped by the what was that? That outlines the risk level of different UV exposure. It's a color-coded UV index that is used to predict risk of sunburn from overexposure. Important factor in UV, deciding UV index is ozone concentration in the upper atmosphere, elevation, where you live, cloud cover, etc. So these things happen if you live in high elevation, you get more exposed to UV. So according to this UV index scale of 0 to 11 here, you can see lower level is UV index 0 to 2. That's the green level, color-coded. If you burn easily, cover up and use sunscreen. So that is a low level of UV radiation. Moderate, little bit higher than low level is 3 to 5. Stay in the shade when sun rays are strongest. Sun rays are strongest between 10 a.m. and 4 p.m. High, 6 to 7. Cover up, wear a hat, sunglasses, use sunscreen, reduce exposure between 10 a.m. and 4 p.m. At very high UV radiation levels, 8 to 10, be especially careful if you are outside on sand, snow, water. These surfaces can reflect UV light. Minimize exposure again between 10 a.m. and 4 p.m. Extremely high UV radiation. Take all precautions against sunburn. Protect skin from sunburn because it can damage in few minutes. Avoid sun between. So just like air pollution index, we have a UV index reported by weather services. I'm trying to get to the next one. Now we're going to look at the different regions of atmosphere and how that, what layer is absorbing UV, etc. Atmosphere is troposphere, the bottom layer, middle layer marked by green area is the stratosphere. The ozone layer is indicated here, ozone layer. Okay, here in that stratosphere. In the atmosphere, air pressure decreases with increasing altitude. Fewer molecules are in high elevation, oxygen and nitrogen. So it's become harder to breathe. You get headache easily if you live in high elevation or go to Mount Everest. Water boils at lower temperature. These are the things. Now we're going to look at ozone layer. Ozone layer located in stratosphere. It's shown up here. Troposphere and stratosphere. The highest concentration is found in the middle of stratosphere. So it's about 20 kilometers, 25 kilometers, or 15 miles from the Earth surface. So normally, ozone layer is a region in the atmosphere with maximum concentration of ozone. There's some ozone in the troposphere produced by vehicular emission as a secondary pollutant. When nitric oxide is produced, it can react with oxygen in the air and produce ozone. Concentration in the stratosphere is 12,000 parts per billion. It's much higher than stratosphere, troposphere level of ozone that we get from pollution. Ozone molecule is triatomic. Ozone is the name for O3, trioxygen. It's a systematic name for ozone. Compared to ozone, ozone in the troposphere. Troposphere has only between 20 and 100. About 1,000 times less ozone in the troposphere. Therefore, anyway, we are not helped by ozone in the troposphere. Mainly ozone that help us is in the stratosphere. Oxygen molecule is diatomic, as shown here. So ozone breaks up when exposed to UVB and produce oxygen and monoatomic oxygen. All right. I don't see the interpreter now. I'm not sure what happens. Okay, I'm going back to here. Ozone is measured in Dobson units. measured in Dobson unit. Don't worry about Dobson unit. Let's stick to parts per billion. Now we done with ozone layer, how it protects us from UV radiation. We're going to look into atomic structure, valence electron, see how we represent different molecules. Okay. I think we discussed it before. Electron atoms have shells. They can only accommodate certain amount of electrons in each energy level. The outermost layer, outermost shell, electrons are called valence electrons. They are important in chemical bonding. Mostly outer shell electrons are the ones that do the chemistry. For example, group 13 element on the periodic table indicate 3 valence electron in the atom. You can go to group 13 and count number of valence electron from the places from the valence shell, 3 electrons. So electronic periodic table allows you to get the number of valence electron. You can watch the video also finding number of valence electron for an element on the periodic table. Reactivity and electrons are related, chemical reactivity. Atoms react in order to complete the valence shell. Normally, except helium, all the inert gases, noble gases, have octet of electrons. It seems like all other atoms are attempting to complete the valence shell. Octet rule is the one that describes stability of an atom with 8 electrons in the valence shell. Electrons are shared between 2 atoms to satisfy octet, which are found in covalent molecules or molecular compounds. Shared electrons produce covalent compounds. For example, hydrogen. Each hydrogen atom has 1 valence electron. They share with each other to produce covalent bond, that line between the two hydrogen atoms. Is sharing electrons. Electrons are also exchanged between atoms, 2 atoms, making ionic bond, produce ionic compounds. There are 2 types of bonds, covalent bonds and ionic bonds. We're going to discuss them in later. Sodium chloride is ionic compound. Sodium is a nonmetal. Sodium is a metal. Chloride is a nonmetal. They produce ions, cations and anions, which are held together by electrostatic attraction, which is the basis for ionic compound. We use Lewis structures for atoms and molecules to explain the sharing of electron. So we're going to focus on writing Lewis structures. How to draw a Lewis structure? from Lewis dot symbol of elements. Let's do an example. These are the steps. Draw the Lewis dot symbol for elements in the formula. First step. Determine the central atom of the molecule. One of them is central atom. They normally make most single electrons. Pair up unpaired electrons with one terminal elements so that valence shell of every atom achieve octet or duet for hydrogen. If atoms are still don't have octet, lone pairs are put into single bond to create double bond or triple bond if necessary to satisfy octet rule. One of the examples is hydrogen bromide, hydrobromic acid. Hydrogen has one valence electron. Bromine has also one. Bromine valence electrons are 7. When you write down the Lewis dot symbol for bromine, that's what you get, this one. So both have lone pairs. So you share that in the molecule here, HBr, between hydrogen and bromine, produce a line here. This line between hydrogen and bromine is called bonding electron pair or covalent bond. The dots and the lines that are found on bromine itself is called lone pairs of electrons. Lone bonding pairs are two different things. Unshared electron pairs, sometimes we call them. Hydrogen sulfide has formula of H2S, 2 hydrogens and 1 sulfur. Hydrogen has 1 unpaired electron in the dot symbol, 2 unpaired electrons for sulfur in the dot symbol. Sulfur normally make 2 covalent bonds. Bromine make 1 covalent bond. Therefore, you pair up with 2 hydrogens to produce H2S, hydrogen sulfide, where 2 hydrogen sulfur covalent bonds are found, 2 of them. You can write them as lines here. Lone pairs. Sulfur has 2 lone pairs and 2 bonding electron pairs between S and H. So that's how you describe Lewis structures of molecules, starting from Lewis dot symbol. Okay. Let's see whether we can, did I miss anything on the other, because I have okay, there's something missing. Nitrogen also is formed by 2 nitrogen atoms. Nitrogen can make 3 covalent bonds. So these 3 are shared between 3 from each, between 2 nitrogen atoms, make a triple bond between nitrogen-nitrogen. Nitrogen molecule has a triple bond between 2 nitrogen atoms. Okay, get to the next one. How to draw Lewis structures. There's another way to draw Lewis structures. Count the number of valence electrons in the total molecule contributed by each atom in the molecule. For example, water. Water has 8 valence electron total, 6 from hydrogen 2 from hydrogen, 1 each, 6 from oxygen, adds up to total of 8 electrons. Add the valence electron contributed by individual atoms to obtain the total number of valence electrons. Now arrange the atoms, place the atoms. This is kind of descriptive. You pick up the central atom and connect terminal atom. Central atom makes more covalent bonds. So you connect the terminal to central. Place electron as pairs of dot to meet the octet rule after you connect the molecules. Start outside atom first, filling electrons. Remember, hydrogen only need 2 electrons. If necessary, form double bonds to meet octet rule. Rule only after all electrons are assigned. Octet rule, check the octet rule, meet the octet rule. Now we going through examples. Covalent bonds are usually drawn with lines that represent the pair of shared electrons. If you start with water, there are 8 valence electrons on the total, 2 from hydrogen, 6 from oxygen. So you can also start with Lewis dot symbol. The connectivity is between oxygen is connected to 2 hydrogens with 2 OH covalent bonds. So the Lewis structure finally is written in this form or this form. There are 2 ways you can write. Sometimes we use dot symbols, dots for bonds, lone pairs. Sometimes we write a line. These 2 bonds are OH bonds, OH, 2 OH bonds are called covalent bonds, shared electrons, bonding electron pairs. For methane, which is in natural gas, you have carbon as the central atom. Why carbon is central? Oxygen is central in water because oxygen makes 2 covalent bonds because it has 2 unpaired electrons in the Lewis dot symbol. If you look at carbon in the middle, which has 4 electron pairs, unpaired electrons, they can combine with carbon with 4 CH bonds. So finally, you can draw the Lewis structure with the dot form or line form here. There are no unpaired electrons. Carbon has octet, 1, 2, 3, 4 bonding pairs. Bonding pairs, each bonding single bond is 2 electrons, therefore all add up to 8 electrons. Carbon has octet. Hydrogen has duet. Therefore, it follows the noble gas stability rule, including octet rule. In oxygen molecule, Lewis dot symbols are shown here. When it forms a bond, there are 2 electrons from each oxygen shared by each other. You have a double bond between oxygen in diatomic oxygen molecule. We talked about this nitrogen. There's a triple bond. Triple bond is 6 electron pairs, so 6 electrons shared between 2 atoms, or 3 electron pairs. Nitrogen molecules has two non-bonding electrons, two pairs of non-bonding electrons, three pairs of shared electrons. Now we're going to draw the Lewis structures for each of these molecules. Hydrogen sulfide. There are two hydrogen atoms and one sulfur atom. Total number of valence electrons is sulfur is 6, valence electron, 1 from each hydrogen atom, 8 electrons, valence electron. In the Lewis structure, you need to have 8 electrons used. Dichloro, 2-chloro means dichloro, difluoro, 2 fluorine atoms, methane. Methane is CH4. 4 hydrogens are replaced by dichloro and difluoro. Therefore, it has to have a similar structure to methane. Let's look at it. We talked about hydrogen sulfide. There are 8 valence electrons here. 1, 2, 3, 4. These are pairs. Pairs has 2 electrons. One pair has 2 electrons. The octet rule is satisfied for sulfur. Duet for hydrogen. Always hydrogen cannot make a octet because it can have only 1s orbitals. So similar to chlorine, methane, carbon in the middle, right here, carbon bonded to chlorine and 2 fluorines. So it's 2 fluorines here, 2 chlorines here. Each has a unpaired electron. Therefore, it pairs up. Chlorine, carbon has octet of electrons now, just like in methane. Also, fluorine and chlorine also has octet of electron. Number of total valence electrons. There are 4 here, 3 from each fluorine atoms. 3 times 4 is 12. 12 plus 4 is 16. How do I get 16 valence electron here? Carbon is 4. 7 is fluorine and chlorine. 7 times 4 is 7 times 4 is 14 times 28. 28 from, am I doing right? 7 times 2 is 14. 14 plus 14 is 28. 32. We had to have 32 electrons here. 1, 2, 3, 4. That's 8 electrons. Let's count the pairs. 4 pairs. 1, 2, 3, 4. 3 times 4 is 12. 12 plus 4 is 16. 16 times 2 is 32. So valence electron number has to be same. That comes from total of that. So this has 8 valence electron or 4 electron pairs. This has 16 electron pairs. So we got to know how to do Lewis structures of covalent molecules. We're going to look into ozone and draw Lewis structures. Ozone show resonance. I'm going to talk about that, what is resonance means in Lewis structures. In Lewis structures or molecules, single bond is shorter or longer as number of electron pairs increase, shared electron pairs increase, double bond, triple bond. they become shorter and stronger. So triple bond is stronger bond than single bond. Bond strength increase from single to double to triple. For ozone, if you look at the ozone molecule, one of the bonds are single, one of the bonds are double. Okay. For example, let's write down the bottom one. This first one on the top here, Lewis dot symbol for 3 oxygens. Each has 2 single bonds. When you fill out, you get the structure here. 1 single bond and 1 double bond between 2 oxygen. So we write down this structure in here, right here, on the right. But the double bond could be distributed in, there's a possibility we could put the double bond in there. That's exactly what happens. In ozone molecule, 2 oxygen and oxygen bonds are not, one of them are double, single, one is double. They are averaged out. This is about 1.5. The bond distance is 1.5. 1 is a single, 2 is a double. Bond distance indicate it has partial double bond character. So resonance structures are needed to describe the real molecule. Especially this happens when you have choice to put double bond in 2 different places with the same number of octet electrons, same number of valence electrons, and without changing the position of the atoms. That's called the resonance. We're going to look into Lewis structures with multiple bond. Carbon monoxide, if you look at this, carbon has 4 valence electrons, oxygen has 6 electrons. Then you connect the carbon with this. This is what we have. So you put the octet into carbon, and so this is total number of 6 plus 4, 10. Here is 10 also. Total number 2 times pairs wise 1, 2, 3, 4, 5, 10. But carbon don't have octet. Therefore, you put the lone electron pair here, you get the double bond. Still carbon don't have an octet. So we put the second one here. So carbon oxygen bond in carbon monoxide has a triple bond. There's no possibility of resonance structures. Why? There's no other place that we can put the carbon oxygen triple bond, only one place. So there's no resonance in here. In sulfur dioxide, if you look at sulfur dioxide Lewis structure, when you draw it, sulfur is the middle atom. Make bigger atom now. When you have both atoms making 2 covalent bonds, pick the bigger atom to the middle. Sulfur is the middle atom here. Bigger atom always takes up the middle central atom as the central atom. So if you look at this, this is octet here. This is octet here. This is octet here. But there's a possibility that we can put the double bond in the other side here. Therefore, Lewis structure of sulfur dioxide has two contributing structures, resonance structures. The real bond between sulfur and oxygen is one is not single, one is double, is between 1.5, 1.5, they're equal, but shorter than single bond. Bond order is between 1 and double bond, 1.5 bond order. So sulfur trioxide also shows the resonance. Now, when you draw the Lewis structure, sulfur is the central atom. Count the valence electron. All valence electrons are same as sulfur is 6, oxygen is 6. 6 times 3 is 18, plus 6 is 24. Now there are 24 electrons in here in the valence structure. We can count it and prove it. So this double bond drawn in the first one could be put in here. Therefore, resonance come into picture, that's just like ozone has resonance. We're going to look into Chapman cycle. Chapman cycle. Let me get to the. There's a set of reactions that take place in the stratosphere that maintain a steady state of ozone concentration. That set of reactions are called Chapman cycle. The UEC here, oxygen are broken into two oxygen atoms by UEC. We told UEC is the highest energy. Some new oxygen, atomic oxygen was fed into this. This oxygen react with other oxygen in the layer, ozone atmosphere, produce ozone. Ozone is absorbed by, this is UEB, are broken into UEB, are broken into oxygen and ozone, or atomic oxygen. Anyway, ozone also can break into oxygen, reacting with atomic oxygen. So this cycle produces oxygen atoms, and eventually they maintain a steady state of ozone in the ozone layer. Therefore, very important, Chapman cycle maintains the ozone levels in the upper atmosphere, in the stratosphere. UV light breaks bond in both oxygen and ozone, but higher energy light is required to break the bond to ozone, bond in oxygen. UVC is the one that breaks up in here, oxygen to atomic oxygen. Let's look at how safe is our protective layer. I'm stuck. Ozone layer provides natural source of protection against harmful UVB radiation, UVA and UVB radiation. Ozone absorb UVB, but still UVA can reach the troposphere and cause problems with skin. Ozone can be naturally destroyed by dissociation of water molecules into free radicals. Ozone can be dissociated with water molecules, but atoms will be unpaired electrons. With unpaired electron, water and hydroxide ion. Ozone can break up water and produce free radicals. But water is not the problem. Water is already there in the atmosphere. Steady state of ozone is maintained. It seems to be third something that is beyond natural sources were responsible for destroying atmosphere ozone layer. Water was not the problem. If you look at the ozone layer in the Arctic region, Antarctic region, in 1979, it was okay. 1988, 10 years after, they started to appear. 1998, it became bigger. 2006, almost same. We began to know the lower concentration of ozone here in Dobson unit. The ozone layer, ozone is getting thinner in the Antarctic region. Antarctic is in the south. So this is the first indication ozone layer in the Antarctic region is going down. The concentration has decreased dramatically since 1989, but varies by year. It's 73 Dobson unit in 1994. So if you look at this diagram, minimum ozone. So it is going down since 1980. It's kind of staying same 2015 in the Antarctic region. Now chemistry became the culprit of producing a lot of chemicals for refrigeration units. Dow Chemicals came up with Freon and came up with air conditioning and made our life easy. But we didn't know that whatever progress we thought we are making also make our detriment. So CFCs, chlorofluorocarbon, carbon compounds containing chlorine and fluorine are non-toxic, non-flammable, inexpensive to widely used refrigerant, cooling agent in refrigeration units. It revolutionized air conditioning and refrigeration industries. Previously, we used ammonia and sulfur dioxide and methyl chloride. So they were smelly, bad. So we thought CFCs were good fit. The CFCs we use in air conditioning coolant is Freon 11. Freon 11 is trichlorofluoromethane. trichloro, 1 fluorine and 3 chlorines in the methane molecule. Also freon 1, 2. 2 chlorines and 2 fluorines. Freon 1, 2. 1, 1 is 1 chlorine, or 3 chlorines and 1 fluorine. Now the problem is chlorine in the compound can break up in the atmosphere and create free radicals. And these free radicals can react with ozone and break up ozone into oxygen and deplete ozone layer faster than the water or natural things does. Although CFEs are inert, that means unreactive, they do react with UVC, react when the UVC radiation in the atmosphere. They at upper atmosphere, they react with UVC, break up the compound into chlorine. The resulting monoatomic chlorine can break down ozone through a series of reactions. Chlorine is used as an early reaction, and it is a catalyst. Catalyst is something that increases the rate of a reaction without being consumed. So therefore, effect of chlorine is bad. If you look at this picture, stratospheric ozone, chlorine, it went up. As it went up, stratosphere ozone level went down. You see that chlorine is red line, ozone is green, blue line. So it breaks up with the UVC in the atmosphere, produce chlorine radical. That chlorine radical react with ozone, O3 here, produce breakdown faster. Catalyst is even bad because catalyst can convert many ozone to breakdown. Now, question is why ozone layer in Antarctica, not in Arctic region? The lower stratosphere over the South Pole is coldest spot on Earth. South Pole is coldest. I'm not sure why the South Pole is colder than North Pole. Maybe air flow up to the North Pole little, the air can go higher up. I'm not sure what the mean that is the explanation. South Pole is colder than North Pole. If you look at the South Pole temperature here, Arctic, in July, August, where they have the winter season, South Pole has winter in July. They are coldest then. Arctic region is red line here. So this cold weather in the Arctic region helped to create polar stratospheric clouds. These are clouds that are caused by sun's radiations. You heard about aurora, that some light in the Arctic region and Antarctic region from the sun's radiation. These are called polar stratospheric cloud. Now these catalyze or help chlorine reaction to break down ozone destruction. Therefore, Antarctic region is severely affected by ozone destruction through the chlorine than the other regions of the atmosphere. Results in a seasonal variation is in ozone hole. There's a dark line here, PST line, polar stratospheric cloud line. Below this temperature, more clouds are produced. So Arctic region don't have that much of a problem, but Antarctic region has. So industry found out that there are problems with ozone destruction caused by chlorine in the freon. So there was a conference meeting in Montreal. They came up with 1987 Montreal Protocol. They plan to ban production of CFC by 2010. 2010 is passed. We came up with different refrigerant coolant, but the recovery of ozone concentration is slow. So this is 1985, 87 in this region. So you are here is 2005. So 2010 here. What is this graph? 1,000 of CFCs. The CFCs is banned here. It steadily decrease. But it takes long time. That is the, I cannot read it. It takes about 2070 to reach the lower level as we had in 1980, 1970. Will take 2000 reach 19 level of chlorine concentration. It's a long process. CFCs are replaced by HFCs. Now chlorine is gone. You still have fluorine. HFCs is hydrofluorocarbon. Chlorine is replaced by hydrogen. Now there's a problem. HFC is a greenhouse gas, but that's not the problem mainly. It also hydrofluoroolefin are another potential replacement. They break down. They are not inert like freon. Olefins. Olefins are double compounds, carbon compounds with double bond. The freon is replaced by HFCs, hydrofluorocarbon. So now chlorine is gone. That's currently being used. You probably heard about that you cannot buy freons anymore. So you have to convert your refrigeration, air condition to new system. Hydrofluorocarbons, olefins, with the double bond, break up easily in the atmosphere before it reaches the upper layer. So therefore, that is safest. Carbon-carbon double bond, making it more reactive, shortening its lifetime in the atmosphere. With the ozone layer weakened, we need to additional protection from sun. So ozone layer, destruction of ozone layer cause more problems. Sunscreens are generally used. There are two types of sunscreens, physical and chemical. Physical is they absorb UV radiation. Chemical is they chemically change when UV radiation is. That's sunscreens on the nose. But sunscreens is physical sunscreen are nanoparticles made from titanium oxide and zinc oxide. They absorb UV radiation. Nanoparticles have dimensions between 1 to 100 nanometers, which are similar to size of antibodies or small viruses, much smaller than cells. They are physical sunscreen. They absorb sun's UV light. Photon absorption. Photon is light absorption. Then when the absorb it and release that heat, therefore effect of UV light is negated. There's no UV light passing into skin. The energy of radiation has to match the energy difference in the absorption. Excited state is after nanoparticle absorb the UV radiation. They are converted to heat, not emitted as UV radiation. The energy difference is dependent on composition and size of the nanoparticles. So this is kind of a technology, physical absorption of UV in sunscreen. Chemical sunscreen contain organic compounds, primarily composed of carbon, hydrogen, and oxygen. They chemically react with UVA and UVB. The red ones are UVA absorbers. Blue ones are UVB absorbers. They have parts of molecular structure alternating double bonds. They can absorb UV and react chemically. So these compounds are in sunscreen. They have double bonds, alternating double bonds. They absorb UVA. UVA is the main thing that we have to stop from sun's radiation. The other part is UVB. UVB is absorbed by, so mostly sunscreen has UVA absorbers and some are UVB absorbers. So third one is third type of molecules absorb both UVA and UVB, the green ones. So there are chemical compounds that used in producing sunscreen. Okay, we're done with chapter 3 today.